Kia ora Year 12. This video is the first I'm going to do on calculus, and we're going to look at differentiating simple polynomials. So there'll be no fractional and negative powers in this one. We'll save that for later on. So let's start by looking at our basic rule for differentiating a polynomial. Here's an example. Suppose I've got f of x is equal to x to the power of 8. So this is my function, and now I'm going to find the gradient function. We say that is f dash of x, and we bring down the 8 and times it by x to the power of 7. So this is called a couple of things, the gradient function or the first derivative. And the process of getting from here to here is called differentiating. Now that's one of the forms of notation we'll see. The other one is y equals x to the power of 8. And if we're using the y equals notation, we usually write the first derivative as dy by dx. Okay, so these two things here are both ways of writing the first derivative or gradient function. So my general rule for polynomials is that if my function is in this form, a times x to the power of n, where a is some number, then my first derivative comes from bringing down the power, timesing it by the a, and then reducing the power by 1. So on the next slide we're going to try a bunch of different ones to get the idea. Okay, so if we've got x squared plus x to the power of 5 is equal to f of x, f dash of x will be 8x to the power of 7 plus 5x to the power of 4. So in each case I take the power, I bring down the power, and I reduce the number by 1. Notice that if we've got pluses and minuses, we just differentiate each bit separately. So number 2, f of x is equal to 5x to the power of 7 minus 2x to the 6. So the gradient function will be 5 times 7, 35, x to the power of 6, minus 2 times 6, 12x to the power of 5. Right, number 3. Let's call it something other than f of x this time. Let's make this one g of x. It really doesn't matter what this is. All we're talking about is the idea of a function that we first came up with way back probably in year 9, right, where we take a value of x and we do something to it. So here g of x is equal to 4x. Now it's surprising how often this one trips people up, but it's because you're not seeing a power of x. Really, this is x to the power of 1. So my rule works as usual. So g dash of x is going to equal 4 times 1, which is 4. And then if I reduce that, I get x to the power of 0. But we know that anything to the power of 0 is 1. So g dash of x here, the gradient function, is just 4. And intuitively that should be starting to all click in together, because this function is simply a straight line. All right, so g of x is equal to 4x, looks like that. And it has the same slope no matter where you are on the curve. Right? Doesn't matter where we do our rise over run calculation, we would get 4. So that comes through, of course, when I use my polynomial differentiation rule. Okay, so now time for you to try doing some. First, let's do these. Let's have h of x is equal to 3x plus 2. K of x is equal to x to the power of 4 over 5 plus 3x, f of x is equal to 5x to the power of 9 plus x cubed over 7, and lastly do another f of x1. F of x is equal to kx squared plus mx to the power of 12. So pause the video and have a go at those. Okay, the first one, we had h of x equals 3x plus 2. So what's h dash of x? The gradient function will be 3, and this constant here differentiates to give me nothing. Okay, if you're thinking about that, you can think about 2, the 2 plus 2 bit is the same as 2 times x to the 0. It's a really strange way to think about it, but it shows you that it fits the rule. So now, if I've got the functions equal to 2x to the power of 0, and I do my polynomial rule on it, I bring down the 0 and I get 2 times 0 times x to the negative 1, which will equal 0. So that's the kind of silly apply the rule way to think about it. The better way to think about it is from a graph, that if we have the equation y is equal to 2, that's just the equation of a horizontal line. And the slope of that line, no matter where you are on it, is just 0. So that's why when you have plus a constant on the end of anything, and we differentiate, it disappears. So the gradient function there is just h dash of x equals 3. The next one, k of x, is equal to x to the power of 4 on 5 plus 3x. Now again, these are pretty unpopular with students when they first see them, because you see a fraction and you don't like it. So when you're starting, it's best to write this out and think of that as 1/5 of x to the power of 4 plus 3x. Now it doesn't seem so bad. You'll get used to doing those without rewriting if you do enough. So here we bring down the power and we've got 4 times 1/5, which is 4/5. So 4/5 x to the power of 3 plus 3 from differentiating that bit. Okay, the next one, f of x is equal to 5x to the 9 plus x cubed over 7. Same idea, f dash of x will be 45 x to the power of 8 plus 3/7 of x squared. Right, because this is 1/7. This bit here, I'll just write this out here, is 1/7 times x cubed. Okay, and I'll do a new slide for the last example. Right, the last one was f of x is equal to kx squared plus mx to the 12th. Right, so here, k and m are just some numbers that we don't know. So the rule applies as usual. I bring down the power, 2, and I times it by that number, so I get 2k. And then it's x to the power of 1 plus, I bring down the 12, 12 times m, x to the power of 11. Now, we don't usually write that little 1 up there, so let's get rid of it. It's just to show you that it's the same rule being applied. So 2kx plus 12m x to the power of 11. Okay, hope that helps. There are lots of practice ones in the New Lake for you to do, and Delta exercise 31.6 and 31.5 are also very good. Thanks for watching.